So we will talk about these technologies today, and hopefully I will present to you an overview of what you can achieve with Docker and Docker Cloud relatively easily with a command line interface and some Node.js libraries. And I hope, like, by the end of the hour, you'll have a complete picture of developing and deploying microservices applications to production with a end-to-end automated build and testing stack and everything included in a single solution, which is almost free for use. So let's start. First things first, I'm Armagan Amcalar. I'm currently working as the head of software engineering at UNU GmbH. UNU is a startup located here in Berlin, and basically we're building urban mobility solutions. We currently have an electric scooter product that we built, and we're quite proud. And yeah, we have a lot of solutions that are in the pipeline for the coming years for electric mobility. And I also invest a lot in open source technologies. I have several open source libraries on GitHub that range from brain signal processing to front-end libraries to microservices and more. So if you are into GitHub, I would encourage you to check out some stuff there. I've been living in Berlin for the last 2 years, and so one of my libraries is called Erste, which I believe means first, because it was my first library in Germany. So I picked a German name because I just suck at German. So what I'm going to talk about today is, we'll start with an introduction of what microservices are. And because this is kind of a buzzword and a hype right now, and I have some bad news for people who are running less than 10 microservices. That's kind of the threshold. Probably what you're doing is not microservices. And today this talk will be about that and the properties of a real microservices approach and architecture. It's just not code. It's not only deployment, but it's a complete package. And we'll give an example of an e-commerce application. Who developed an e-commerce application before? Very few. Like, you're really lucky. It is, it is maybe the worst thing in a developer's life to build for an e-commerce application where you have catalogs, payments, stock management, etc. You are really lucky, and I'm glad. But it's one of the most common scenarios of application development. So the example will be about an e-commerce application where you can see how microservices would fit in there. And then we will talk about some code with Node.js and how we can accomplish a microservices application in Node.js. And briefly talk about Docker and what it brings to the ecosystem for basically making this a reality. And in the end, we will have a demo section where I will show you an example application, an e-commerce application that is built using all the technologies that I mentioned. So let's start with what isn't a microservice. So probably most of you have like email notification systems that send notifications to the user or to your developers as a result of an action. Like, hey, you bought something, here is your Quittung. I don't know what the English word is anymore. Or here's your Rechnung, whatever. So most of those systems rely on queues. And they work with RabbitMQ, ZeroMQ, whatever, or SQS. And they are not really microservices. They have been around for a very long time. Like, we've been developing asynchronous applications with queues forever, like for years. And microservices is a little bit different. And of course, after this, I'm going to talk what it actually is. But if you're using your services with queues, it's not microservices. Even if you have 50 different services for payment reconciliation with payment providers or timing out certain use cases, it doesn't quite add up. And just because you have multiple programs or software running on the cloud or separate servers and that they communicate over HTTP, over REST API, again, doesn't really mean, yes, it's some kind of services. And it might be the service-oriented architecture that we've been used to for years, like since 90s, but it's, again, not microservices. So there are a huge crowd over there screaming about microservices, and there is a lot of misinformation or disinformation about it. And basically, this whole presentation is to clear that up. So what is a microservice then? Basically, if you're breaking down the fulfillment of a single client request into multiple collaborating services that run in separate containers, in separate as separate programs, then you can call it a microservice. So this is the baseline. And if you're doing this, if your client, a mobile app or a web page, doesn't matter, sends an HTTP request to your server, and then that HTTP request is broken into several pieces and fulfilled with the collaboration of multiple services, like let's say you're doing a payment request, or you want to purchase an item in an e-commerce application. So there are a lot of stuff involved, like we have to check the credit card, we have to check that it's valid, that we can deduce the money, we have to check the stock, we have to decrease the stock, we have to let finance know, we have to let the user know. And there might be a lot of business rules around this. For example, if you're in another continent, we will apply like 30 euros more for shipment. And like all these things should live in separate services and separate programs, because actually they are separate concerns. And we actually have a very nice architecture already that we employ in our software for this, and it's called domain-driven design. Who is familiar with domain-driven design? Yeah, almost everybody. That's pretty good. So domain-driven design is actually the best way to split your application into microservices. I'm really fortunate that all of you are familiar with domain-driven design. But basically, the granularity of each service should be at the domain level. So for each domain, you should at least have one service, and maybe multiple, depending on how complex the domain is. But you have to keep in mind that the domains are the boundaries. So instead of calling as a service class from that domain for getting the user information, you should basically be making that request to the user service, which is a microservice, an application living on its own program space, and then get the response from that. So probably by now, most of you know that in microservices, we are a fan of like having separate databases, having separate collections or tables for our services. And that's true. That's also related to domain-driven design. You should have separate databases for each domain, basically. And there should be no code sharing in between domains. There should be no database or data sharing at the raw level. But you should be using APIs. So I guess this will be, we will exemplify this when we go into the e-commerce application. But if you want to draw the homepage of your e-commerce application, for example, you have to get the catalog, you have to get the user details, you have to get the prices, and maybe the stock information, because some items are not available. These should depend on multiple services, basically. And although it's a single call from the client, the browser, that should be broken down into multiple microservices to fulfill this. And there are several other best practices about this, of course. And the biggest thing is there will be change. And this is a topic of another huge discussion and maybe another session. But microservices is not about writing code only. It's not about how you structure your apps. It's also how you structure your teams and your organization around it. So you have to embrace change. Everything will change, starting from the code and the API versions of your internal services up to how you design your team hierarchy, like who is reporting to whom. And it all boils down to giving autonomy to your teams and to your services. The product service or the payment service should belong to a team, and that team may choose to implement it with Go, with Python, with Java. You shouldn't care, because you should have a single API interface, which is usually a REST API, but you don't have to. And then they are free to do whatever they want. So this basically is a challenge to regular organization schemes, and it's really hard to embrace microservices plus DevOps because microservices will not exist without DevOps. You should have like 50 or 100 services running at the same time. You have to manage this. This is a huge complexity, and it only comes with embracing change, autonomy to the teams and individual contributors. So you have to automate testing. You cannot rely on manual testing anymore because there are a lot of parts moving without you knowing even. You are doing regular deployments to production multiple times a day from different teams, and you have to make sure that they stay in sync and like nothing is breaking. But obviously, some things will break, and you will not be able to prevent that, which means, okay, you need to have very strong monitoring and rollback mechanisms in place. And it's really easy to roll back a monolith application. You have a single application anyway, you just roll it back, and you're fine. If you have microservices and you have 50 services and you have to roll back 10 of them to a previous version, now you have to make sure that they still can work with the other 40 services that are in production that you don't want to roll back. And the API footprints are the same and they can function. So this relies on a lot of automation and a lot of testing. Basically, another thing is how you manage servers. Up until this point, we mostly managed our own servers and we knew them by name. We did SSH and configured them over the terminal or whatever. With microservices, with that many services running in, you have to scale up and down dynamically. And now you cannot manage your servers yourself anymore. You shouldn't know your servers by name. You shouldn't have SSH access to them. You shouldn't configure them manually or whatever. This principle is called favor cattle over pets. Pets are cats and dogs you call by name, you love them, you care for them, and you don't want them to die, obviously. Cattle is a herd of animals like sheep or cow. You mostly care about how many you have and their output, how much milk you get out of them, how much meat you get out of them. If one dies, it doesn't matter. You'll replace them because they are also reproducing. Of course, this is an analogy. But still, what is important for a mass production system is they don't really know the names of each cow in their farm. They just care about the count because it replenishes over time. So this is how you should manage your servers. You should only care about what resources you have available and if you want to scale up or down, and the rest should basically be automated. So here is a very broad overview of an example e-commerce application, which doesn't have to be an e-commerce application, but will also apply to other domains and other applications as well. You surely have a load balancer, which I call in this graph an API gateway, which is responsible for serving the requests for the clients and for routing those requests to the services in the backend. You might have an admin interface, you might have an end user interface, which your clients will talk to. And behind the load balancer or the load balancers, you have a host of services that act in their own domains. For this example, we can have a purchase service, we can have a payment service, a user service, and a product service, working in combination to make an e-commerce application. So if you notice, all of them have their own databases. And for example, you want to let the user make a purchase, and that's fine. The purchase service should know about the user, like who is making this, this purchase call, the user ID, and what are their payment information. So you give the user ID to the purchase service, for example, in your call, and the credit information, and the purchase service would go to the user service. Hey, I need this user detail to basically make a purchase, and the price is this or whatever. Like, give me the credit card information, or give me whatever payment information they have, and it takes this info from the user service and passes it on to the payment service, saying, okay, like they want to do a software payment or last shift, and this is the bank information and details, just do it for me. And it gets a confirmation from that or not, depending on your application, of course. But the idea is basically all of them have their own databases, and you break down the fulfillment of a single request into multiple service calls that happen in the backend. For example, the product service may not have to depend on anything else. You can ask it for a list of products, let's say in your catalog, in your stock. I didn't put a stock service here. Obviously, you would have one in real life, but this is currently included in the product service. Okay, it goes to its DB, fetches the product list, and returns it to you without asking any other service. It's still a single domain. It's still responsible for that domain, so you can still call it a microservice. So a good example of a microservices application, or a good property of it, is auto-discovery. What happens when you introduce a new service to your application, to your environment? You shouldn't be redeploying your application. You shouldn't be redeploying or restarting the whole system from scratch. What should happen is, and in this case, we have a new log service coming in, but it could be a stock service as well. All the other services should automatically discover that, hey, there is a new kid on the block, and it's doing this feature. Okay, now I can connect to it, and maybe I can stream my logs, or I can stream my notifications to that without redeploying any other service, product, purchase, whatever. This is really hard to get, and it's really important, but it's something what Kubernetes, Swarm, or other orchestration services try to give you kind of out of the box. Another good feature or property is a microservices implementation should be zero configuration, which means you shouldn't have to configure IP addresses, port names, file paths of where you want to save stuff. They should be automatically handled for you. And when you couple this with auto-discovery, whenever a service comes online, all the other services will know its IP by default, or will know its host name by default, and they will reconfigure themselves automatically without you going into manual configuration. This is, again, a very hard trick to do, but some of the tools help you with this. But basically, who remembers the time when we wrote the IP addresses of the production machines that we want to deploy? Okay, awkward. You can be broad about it. Don't worry. Everyone did that. The thing is, in your continuous deployment, when you wanted to scale up a production machine, you had to change your continuous deployment script and make a new deployment, because you were adding a new IP address to that pool, and because it would deploy there. Now, this is a problem with microservices, because the idea is you don't have huge vertically scaled machines anyway. You'll have tens of really miniature machines, like 512 megabytes of RAM each, and 20 of those, 30 of those, and they will die. AWS will kill your servers, or DigitalOcean may kill your servers, or you may want to kill them yourself by scaling up or down. And this will happen in a day multiple times. There is no way that you can configure this manually. So this thing should be zero configuration and automatic. So the thing is, I want to run multiple purchase services, or I want to run multiple payment services, because there is a high risk that one of them will be down at a given time. So basically, I want to increase the availability of my services, and the load balancer should automatically know which of those are available, and then redirect the incoming requests for those. And basically, you should include highly redundant systems in everything that you're doing. So the difference between these two slides is basically the product service, user service, payment service, and log service. They are all multiplied. You have to have a redundant system if you want to do microservices, because things will break, and they will break more when you really use really low resources. And you can't rely on manually, creating a new server or bringing it up again or restarting it. It should be automatic, and it should be highly redundant so that you're running, 10 copies of each service, and you don't care because they're really, really cheap. Another property is things should be fault tolerant. What happens if one of your payment providers stop responding to your API calls when you're building a monolith application? Basically, your application freezes because you will create a new thread for every incoming client request, and that thread will block until your payment processor gives you a response. And, well, you're stuck because 1,000 people are trying to pay, and you filled up your server by basically doing nothing because the payment provider doesn't answer. And now your users cannot browse your web page even. They cannot see the catalog, which doesn't really depend on payment. But you lost your system, basically. You have to restart. You have to realign your whole monolith around this. Microservices give you the advantage of breaking down the requests, which means if your payment service is not working, if it doesn't respond, it doesn't matter. The product service is there. Other parts of your application will be online and accessible, and users will be able to use them. So your services shouldn't fail, or your website or your application shouldn't fail just because one bad service that stopped responding. But of course, what follows is a self-healing mechanism. This also should be automatic. It might be that you lost a data center in AWS, and it might be that your application will not, or that servers will not be live for the next 2 hours. Of course, you cannot sit and wait it out. You have to act. And the good thing is, you don't have to act automatically. Like, your orchestration system or your automation should actually put that payment service into another machine, into another data center automatically. You cannot manage this by hand because, again, like we have 4 services here, but you'll have at least 50 or 100 of them in your application. And actually, like big companies like Netflix and Airbnb, I'm not even talking about Google or Facebook, they are talking about services, the number of services on the order of thousands. And like they are not copies of each other, they are different services. And it's really impossible to manually manage this. So there should be a self-healing mechanism that will say, oh, well, we lost the payment service, but my task should be to have at least 3 payment services active all the time. So I should basically do whatever I can and respawn a payment service in another data center, in another server, I don't know, but I have the API keys to do that, so I will just scale out on my own and maybe let the DevOps team know, hey, there was a problem and I just scaled it out automatically. Like, this is the orchestration system you need to have in order to build microservices. So these are kind of the 5 best practices and properties of microservices. And now I want to ask again, and again, no stress, it's normal that you don't, but how many of you are doing these things in production? Okay, very few. And they are the people who are really running microservices. And this is very hard to get unless you're using the right tools, unless you're using the right methodologies. And we will see in this presentation an example of how to make this happen. So, okay. So here's an example in Node.js. And this is using a library called cote, which, as a disclaimer, that I built to enable microservices over 4 years ago. It basically gives you all of the features out of the box without any configuration. Basically, you don't do anything other than, for example, what is written here. Who is familiar with Express? The Node.js HTTP server? Okay, not many people. But it's a very easy tool for building HTTP REST APIs. And here you basically see an example of such an Express application. What we do is basically, this is a user-facing API, and it fetches the list of users, or it fetches a single user. I hope the syntax is clear enough so that you can follow what's going on. But basically, cote builds on the idea of requesters and responders and publishers and subscribers, which means if you want to make a request, if you want to forward, let's say, this get users request, you should create a user requester, and there should be a domain service which is related to domain-driven design again. A domain service like a user service, which should respond to that. And in the example above, basically you see such a domain service and what it should do. This is all the code that you need. You basically require a model, which could be anything, Mongoose, Waterline, ORM, whatever you want to use with Node.js. And basically you create a new responder, and on list, you forward that to your model. On a GET request, you forward that to your model. On a CREATE request, you forward that to your model. Obviously, this is a lot simplified, but there are no configuration involved. And another application that should run anywhere else in the world will basically have a requester, and it will just pipe these requests, the get user request, send the ID parameter, and it will be sent to the model. The good thing here is you can deploy this anywhere in the world on different machines, on different data centers, and they will work. You don't need to do anything about this. There are no configurations involved. There's only one thing that you need to have, and that's a virtual private network. So as long as they are on the same network, they will find each other, they will communicate with each other, and they will work. And we will see an example of how to realize this with Docker Cloud. Docker Cloud, Kubernetes, they all give you this overlay network, virtual overlay network for all of your services. And simply, you can have some machines in DigitalOcean, some machines in AWS, and they will still be able to communicate with each other, again, without any configuration involved. You do nothing. You write no code for it. There are not even ports here. Like, you don't listen to, hey, 8,000, and you don't have to think about what happens when the ports clash, because there won't be such a thing. So, a very brief intro to code and its properties. It basically doesn't depend on Redis, it doesn't depend on queues, it doesn't depend on anything else. It's just a single library that you can use in your Node.js applications, which gives you zero configuration, no ports, no routing, and there are no fixed parts, like no message brokers, no manager nodes, so that you won't lose your application when they fail. It's a decentralized system. It uses auto-discovery without a central bookkeeper, which some of you may have worked with, etcd or something. And it basically, it's also fault-tolerant. When some of the services go down, some of the responders go down, it just waits until another one is there, is open, and forwards that request to a new one. So you don't lose your requests. Since it's zero configuration and decentralized, you can scale it horizontally to whatever machine you want. When you create a new machine, it will get deployed to that new machine, and it will start working with all your other services without any problems, without any configuration at all. And obviously, it's also built for performance. And the good thing is it has a very human API. It's really, really easy to use, and you don't have to deal with, hey, should I use put or post here? What was patch for? Or is it a delete request? Or is it a post request to delete something? Basically, we use human messages. And yeah, there are a few examples here, but they're not that problematic. Basically, you can use any string. So how does Docker come into this picture, or Docker Cloud? The good thing is they give you an immutable environment, which means you don't manipulate it by SSH connections or anything. You just deploy it as a single YAML definition, and you can version control it also. And you can delete it or recreate it from scratch. It will be the same thing. Your dependencies will remain the same. Not that you, for Node.js environment, you have the package lock JSON thing. Your Docker images will remain the same. Basically, you will get the same thing wherever you deploy, regardless of the running host machine. It's basically an immutable environment. It will give you an overlay network, so your different services and servers can actually communicate with each other without any configuration at all. There is a tool called Docker Swarm, which gives you huge capabilities for orchestration, for automating the orchestration tasks. You can scale up or down individual services. You can scale up or down machines or a cluster of machines with just one-line commands and very easy to use. You can roll back to previous versions of some of your services, and you can pass around secrets like keys or tokens as environment variables. And basically, maybe one downside is it requires some manager nodes, a manager cluster that you shouldn't lose. But there are automated solutions for that to make sure that at least, like if you're on AWS, it's running on multiple availability zones or multiple data centers even. So you won't, it won't be doom for you when one data center fails. But its goal is to make the definition of your service as a YAML file, the definition of your application as a YAML file. The goal of Docker Swarm is to make it happen in real life with whatever tool it can use or in whatever way it can do. Docker Cloud is another solution provided by Docker. It's a kind of like a software as a service for this whole thing. It was another tool called Tutum, and Docker bought them, and now they are kind of rebuilding it from scratch with Docker Swarm. And it has a very nice UI that I'm going to maybe present as well. And basically, whatever I told you up until this point in the presentation, Docker Cloud gives you out of the box. It can work with AWS, it can work with DigitalOcean, Azure, or you can bring your own device, you can bring your own servers, and like even if you're running in your own data center or in your own infrastructure, you can use it. One of the most important things is it kind of eases the continuous deployment and continuous integration. You give it your source repository either through GitHub or Bitbucket, and it can access your private repositories as well if you like. It automatically builds the Docker images out of those repositories, depending on the tag or the branch that you push. So if you push something to a branch, an image gets automatically generated, and since it's in the Docker Cloud ecosystem, the related services get redeployed, and the others don't. And basically, it's a very easy mechanism for building your code. It also includes automatic testing. So before building or after building each image, it just runs some shell commands to make sure that the image is up to your standards and it's working, that it's corresponding to your API definition. And of course, if it fails, the build will not continue. So you have testing covered there as well. Anybody familiar with Docker Compose? OK. Docker Cloud has a stack file that is very similar to Docker Compose, but it's unfortunately not the same. But again, they are rebuilding it to exactly match Docker Compose syntax. But it's, again, very similar. And since it's the same team now, they share a lot of ideas. It gives you Slack notifications out of the box. So it has a lot of HTTP hooks, webhooks as well that you can use for monitoring and for to get an overview of your environment. And it can scale, again, your containers, your services up or down with just simple UI clicks or a very nice command line interface. It gives you terminal access to your containers, even if you don't have SSH. Like if you absolutely must have to do it, like there's no way that you cannot live without a terminal access, you can do it over the web browser, even for each container. And it automatically scans your Docker images for security leaks and notifies you as well. This is a paid service, I guess. I'm not using it because I'm using other tools, but it's, again, a nice feature to have, basically, because also if you're running in the enterprise, you should be careful about your security. So now I will demo an application, an e-commerce application that I have built using these techniques, cote.js, Docker Cloud. And these are the URLs that you can visit right now. Most of you have your computers here or your phones. It will just work for you. Just go to these links, and we can play around in kind of a very dummy e-commerce application. And there's also some monitoring included. So for example, this is the interface that you'll face when you go to either admin cote.js.org or end-user cote.js.org. This is a very basic, very simple e-commerce application that runs in real time. So I don't have to refresh. Like you see, the users are coming in. Basically, since it's a very dummy application, since it's a demo, whenever you refresh the end user, you'll simply get a new user in your system. Like I'm user 5, I refresh, I'm user 6, and you'll see that they are updating here in real time. And you'll also see that some people are adding new items to the stock, and it appears automatically on my end user interface, and I can buy them, and I will see that it's updated here in real time. Hey, these are the purchases that I made for five items, the ideas of the items. And I can also see the list of purchases here. Again, I have some balance control, so if I buy a lot of stuff, I'll run out of money. And basically, the idea is there to demo that this is an application with multiple microservices. Now I can't buy anything because I used all my balance. With multiple microservices and a real-time system, and it's really simple to build. Unfortunately, the delete button doesn't work here. I don't know why, but this is all open source on GitHub. I would encourage you to check it out yourself, and maybe you could help me there. I will look into that later today, why it's not working. All right, so this is basically what we see on the interface, and maybe the monitoring interface. This is a D3 application. If some of you have worked with D3 before, let it be known that I hate it, and it's impossible to make a good application with it, at least with my abilities, because if you just, this is just a rotating ball of services, and it's like I cannot stop them unless I click on them. So basically, the yellow ones are the containers that are running in the system. Sorry, the hosts that are running in the system, let's say the machines. And then you have services in each of them. So this is the admin service. It has an admin server that's an HTTP server that I'm sending, like create this product or list the users. And it has some, stop, come here. Okay, stay there. It has some, for example, purchase requester to list the purchases. And it is connecting to the purchase service. And the blue one is the service itself. And it has a purchase responder that is responding to the admin purchase requester. And obviously, the user service is also here. And the admin server is also connected to the user service. So basically, this gives you a topology of all your services running in an environment. And you can see, and this is live, obviously, you can see how you scale up or down, what is lost, or what are the active connections in between your items. Let's show some code. But before that, how do you feel up until now? Is it good? Did you like it, maybe? No? Very little? Okay. It's a bit awkward for me if you didn't really like it. All right. Would you like to see Node.js code, how to make this possible, or Docker Cloud environment, how to deploy this and scale this up or down? Code? Okay. Environment? Cool. I have enough time to actually show you both. Fortunately. If you remember the slides, basically this is the full-blown version of that service, the user service. What it does is it responds to a create request, and it publishes updates when a new user is created, so that the end user or the admin interface can understand that there is a new item. The good thing in code is there is a component called sockend, which gives you a WebSocket interface to all your services, and basically the end user application, which is a single page application, is a single HTML file. It uses socket.io to connect to products and purchases, or a user, and this is an Angular application. So if you want to make a purchase, what we do is we just emit a buy message to the backend, give the user ID and a product ID, saying, hey, I want to buy this, like this user wants to buy this item. And if it's successful, then we refresh the list of items. Now, this is all the code that you write on the front end. You just define a purchase service, which is a socket.io connection to a namespace. And then you do nothing, and it automatically, magically, ends up here in the purchase service. This is the only code you need for the ecosystem to work with WebSockets as well. You just create a new responder. You say, hey, this can respond to the buy command. And like this is just a regular event handler. If there's a buy command, do this. This is a callback hell, which will be fixed with async await keywords in JavaScript, which is really bad right now. But basically what it does is it gets this buy request and fetches the user. And so first creates a payment process, fetches the user, says, hey, this is a new purchase. And like this user is the owner of that purchase. And this is the product that is related to that purchase, save it, and finally, when you're done, just give it back to the user. Tell the user that it's done, that they could do the purchase, and publish another message, which is called update purchases, to the backend, to the back office, so that the back office can be notified of this purchase. Again, there is nothing else, no configuration, no servers, no listening, and it's just this. Now, how do we make this happen with a Docker Compose file? Again, this is all available on GitHub, so you can later on play with it, download it, or check it out, or deploy it to your own servers. We support Kubernetes, Docker Compose, Docker Swarm, and Docker Cloud. So here's a purchase service. Basically, it's just a Node.js application. That depends on the database to function, of course. And the admin is an Express application that exposes some virtual hosts to the load balancer, and the load balancer automatically gets it. And the base is basically an image name and some environment variable. But that's all. Basically, again, this is all running with this Docker Compose file. The Docker Cloud YAML is a little bit different. For example, it doesn't support the extends keyword in Docker Compose, so you have to copy and paste all the environment variables to all the services. But it's pretty much the same. You give it an image, you give it some tags on where you want to deploy it to, and some deployment strategy. For example, this is called every node, which means, hey, I have a cluster of machines for the payment, and now there's some load on my servers, and I want to scale that cluster up. I want to create new servers in it. OK, I will run a single command that I will demo. I will run a single command, and this thing will basically be deployed to that new machine as well. Let's see. Where are we? OK. No, I don't want to print you. No? OK. So you're running. You're seeing the node clusters that I have in Docker Cloud right now. I have one for payment. I have one for other services. I have another one for database. And I have a load balancer on front that basically proxies all the requests. The load balancer doesn't really have to be there, but since this is an HTTP application as well for the backend, we needed that. So you see that they all have a single node here. So a payment node cluster has a single machine running it, and it's deployed on DigitalOcean in one of their data centers. And I hope you can read this, that it's not too small for you, but I have some services that are listed here, a product service, purchase service, and basically their status and where they are running, the Docker image, when they are deployed, whatever. So I want to log the user service output. So this is a live output that's coming from the user service. I hope it's legible. But basically, it logs every request that's incoming. So I will just clear the logs, and if one of you, ladies or gentlemen, could go into the end user interface or an admin interface. Yeah. So thank you. Basically, we're seeing the incoming requests that are being logged. And now I want to scale this because, well, I believe there is some load that you're creating there. Docker Cloud is a nice command line interface that I have aliased as DC. DC services scale user service 3 will give it an error. because it's DC service scale. Okay. Nice. Since I'm running it in every node assignment, I cannot manually scale it up. This is a good thing. Like, as a DevOps engineer, you want to scale some things up or down, and the system says, no, don't basically mess with whatever I'm doing. But I can introduce a new server here. So Docker Cloud Node cluster, let's scale the payment service up. Payment scale payment 3. Now, okay. If you notice the top line, the payment node cluster is getting 2 new machines deployed, and it's currently scaling. Oh, here we are. It's currently scaling up. What will happen in a few minutes? It will create new machines in DigitalOcean, because that's where this node cluster is. And basically, it will scale the payment service up to 3 machines, 3 nodes, so that basically we'll be able to see more requests. So let's log the payment service here. DC service logs -f payment service, and this is where we are right now. Could you make some purchases? Okay. Should I? Okay. So there are some payments that are coming in. And obviously, this is creating a new machine from scratch, putting Docker on it, on the new machine, and downloading my Docker images of the service, and it will start that. So that's why it's currently taking a couple of minutes. We can take this time to actually see what the interface looks like. Okay. So there's the stack that I'm working, code workshop. And there are the services that are currently up. These are the node clusters that I have. The payment node cluster, oh, it's all deployed. So I have 3 nodes running, and in each node, I can see the containers that are running on that node, and I can go to individual containers and see their logs of what's happening. Let's see. Yeah. So yes, it's now deployed, as you see. So you can either use the CLI or the user interface. Now let's stream the logs again. Oh, good. Living on the edge. Okay, so the third one is still deploying onto that node. Yeah. So this is the auto-discovery that I'm talking about. Some things got deployed, and the payment service just discovered it. Hey, there is a new payment service that's online. Let's see if... Yeah, cool. Now you see I have 2 payment services. And when you make a payment, which we did, like the process commands are payment commands. Now, some of the requests will be forwarded to the payment service 1, and the others will be forwarded to payment service 2. And the third one is also up. So again, these are machines running with half a gigabyte of RAM. So they are really throwaway machines, and that also may be why the deployment is taking so long. Obviously, we wouldn't run these in production. But yeah, now you see messages from different payment services. If you do some purchases on the end user interface, yeah, we see the logs that are streaming from different services, basically. Payment service 132, 132. It's a round-robin fashion. And yeah, all I did was a single command, DC node cluster scale payment 3. It created 2 new machines, redeployed the services automatically, without anything else, without redeploying the rest of the application. And the requests are now load balanced directly from the end user interface. And this basically marks the end of the presentation. Thank you. You can find the slides online, like these slides and the demo. And we have a Slack community if you'd like to join us. And let's keep in touch. And I can, I guess, answer some questions. We have 2 minutes, I guess. Yeah, please. OK, so the question is, how do they discover each other? Basically, it uses the same mechanism that Apple TV and other auto-discovery devices use. It's called IP broadcast or IP multicast. It's a feature of every router, except cloud routers like AWS. You have to have another overlay network mechanism. But basically, you broadcast an IP package to the router, and it redistributes that package to different machines that are connected to it. And the same with virtual networks as well. If you have a virtual network, this thing will work the same way. And they discover each other through IP broadcast or multicast, and then fall back to a real, regular TCP server and client connection. And the rest is basic, doesn't really depend on multicast. But the discovery is either multicast or broadcast. Any other questions? Oh, please.
You use framework code.
Yeah.
What did you think about signature?
Sorry?
What did you think about signature framework?
Seneca? Yeah, OK. Yes, I did. But Seneca is not zero configuration. And I also didn't like the API, personally. It's a matter of preference. And therefore, I created something that only depends on a few methods, send and on, and no configuration, no ports, no IP, no services, no service names, no method names, just a few strings. But yeah, I know it's a very, very used framework, which gives you some of the 5 features that we need to have. Therefore, like a combined solution is with Docker Cloud or Swarm or Kubernetes plus code, you basically get everything out of the box. Any question? No? Please.
In Docker Swarm, there's a problem to auto-scale services. Is this possible in Docker Cloud? I do not want to log in every time and scale the services up and down manually.
Yeah. Yeah. Well, yes, there are some webhooks that you can, for example, connect to New Relic, and it scales automatically about, like, if the load is about 70%, you make a post request to the webhook, and it will scale up. And it works. It doesn't work for downscaling. There is no webhook for downscaling, but there is a webhook for scaling up. All right, thank you. I'll be around for some more time. If you have any questions, we can meet outside. Thanks a lot for joining me.